All right, so this course is about Lie groups and Lie algebras, and we start with Lie groups. So we'll just start with definition. By definition, G is called a Lie group, is a Lie group if well, it is smooth manifold and these two things happen. First of all, multiplication map is smooth, so this map M from G times G to G, which works like this. It takes two elements, G and H, and just returns a product. So this map we require to be smooth. And second of all, well, of course, I want it to be smooth manifold and a group, right? So this is a group in abstract sense. So we have this multiplication there, and also we have we can take inverses. So we have a map I, which is map from G to G, and takes an element and gives me back G inverse, and I require this map to be smooth. So idea is simple. You just blend two things. One is you would blend one thing is a group and another thing is smooth manifold. So you require your group operations to be smooth. And it turns out to be very, very rich structure, which is very interesting to study, and it appears in many places. And right away, let us see some examples just to think about something, to have them in our heads. Well, maybe before examples, so this is a smooth manifold, and over what field? I should be more specific. So our field always will be either R or C, right? And if I say it is just any group, then usually I think of this as a smooth manifold, real manifold. But I can add complex Lie group, right? So I can add word complex here. And this means that G is complex manifold, so it's over C, and your transition maps are holomorphic. And instead of smoothness, we'll talk about complex analytical holomorphic. So these are actually two cases, real Lie groups and complex Lie groups, and we'll try to think about both of them. But at some point in the course, some proofs will work only about for real Lie groups, and you need some additional things for it to work for complex, and we'll discuss it. All right, so examples. So there are very simple examples. For example, you can consider just real numbers with addition. or you can consider as well complex numbers with addition. So these are all, of course, Lie groups. You can take instead of addition multiplication, but in order for it to be group, you need to exclude 0. So I will denote it like this, right? So this is r minus 0, right? With an operation here is group operation is multiplication. And another, you can also take C star, which is C without 0, also with multiplication. This will be a Lie group. Right. So third example is circle. So you think of a circle as a subspace in complex numbers. So all complex numbers such that their absolute value is 1. Of course, it is topologically and geometrically it's a circle, and you can multiply, and it's closed under multiplication. Multiplication taking inverse is continuous. Okay, number 4. This is very important example. It is a group of all inversible linear transformation of n-dimensional vector space over K, right? So you can think of it as a matrices, n by n matrices, with entries in K, such that the inversible that is determinant is not 0. This is the manifold, right? And your multiplication is just polynomial in entries, and taking inverse are rational numbers, where in denominator you have the determinant, and therefore in denominator you have something not 0. So this is also a smooth map. So it satisfies our definition. Okay, and well, we can also consider, for example, affine group. This is all transformations of this kind. X goes to AX plus B. So here X is an element of, well, K to the N. A, so, and here, so this is set, as a set, is all transformations of such kind, where we run over invertible matrices A. So A is from GLN, and B is also from Kn. So this is an example of semi-direct product of Lie groups, but we'll talk about them on seminars. All right. So I think well, since I mentioned semi-direct product, let me, as a sixth example, give you this. So if I have two Lie groups, then G1 times G2 is, of course, also a Lie group, direct product. Okay, I think it's enough examples. Some other examples will discover them as we go further. Okay, so now a very important example, a very important notion is Lie subgroup. So let us define it now. So definition, another definition, the second one, that H inside G is called Lie subgroup if two things happen, and we'll have a bunch of definitions in the same fashion, right? So we're talking about smoothness, and we're talking about group structure. So it is subgroup as an abstract subgroup, and second, it is submanifold. So H is a submanifold. Of G. Oh, okay, so the question is, what is submanifold? Because different books call submanifold different things. Now let us be more specific. So question: what do we call submanifold? And this is important. So we call submanifold something which is actually so which is usually called embedded submanifold. So the precise definition is the following. And you can define it in different ways, they're all equivalent, so let me choose to define it like this. So Y as a subset of manifold X is a submanifold if for every point Y in Y, there exists a chart phi, chart phi of X, right? Meaning that it is a map, right, from open set in X to Kn. Right, and I would like my Y to be inside this U, Y to be inside U, and I would like to have some specific condition on this phi, is that if I take phi and consider its image, image under phi of U intersect with Y. So U is actually X, so intersect with Y and see what happens. And what happens should be a slice, right, of, so phi of U is here, it's open, some open neighborhood, some open subset in Kn, and I would like it to be some slice by some linear subspace in here. So here m is less or equal than n. So this is usually what's called slice condition, and I use it to define what is submanifold. Right? So you can find a chart, right, which becomes a corresponding chart for your submanifold, right? And you just restrict it to, say, first m coordinates. So that's what is happening here. All right. Again, examples. Examples of Lie subgroups. Right, so for example, you can take S1. It is submanifold. It is Lie subgroup of C star. Right, this is C star. So this is submanifold in here, and also Lie subgroup. So if you take a circle, right, you take some chart around the point in a circle, right, and well, this slice by lower dimensional subspace, right, and well, let me give you example of something which is subgroup and which is actually manifold itself, but in a subspace topology, so this condition is violated. Okay, so this is not a submanifold. So maybe the easiest notion of not submanifold is the following. You can take, so example, so here we'll just have another example. So this is example of, so not manifold, submanifold. Okay, let me go here. So consider, so take an interval from 0 to 1 in R and map it to, this is a standard example, like which is called figure 8. So map this to figure 8 in R2. So in R2 you can draw something like this. So your ends go very, very close to this point, right? And topology and manifold structure let it come from here. But in subspace topology, this is not a submanifold because this point is the trouble. You can you see that in subspace topology only so your open subspaces, they always look, if you go back, they always look like this. So you have here and something at the ends, right? So ends are also included, right? But you will never get just image of this as an open subspace here, and this is the problem. And so you see that if I take any map in here, right, this will never be something sliced by just subspace. You will always have these ends which are here, right? And so, well, this is not Lie. This does not have structure of group, but this is an example of something which looks like a submanifold, but it is not submanifold. So when we're looking for Lie subgroups, we're looking for subgroups in which this situation doesn't happen. So this is an example why we need this condition. So maybe I can give you actually an example of something which is so example of something which is subgroup and actually has manifold structure, and it is what is called immersed submanifold, but it is not a Lie subgroup. So example of subgroup, so or subgroup, which is not a Lie subgroup. And this is also a classical example. So when we will try avoid some situation, we will always refer to this example. So you can consider torus, which is S1 times S1. It is a Lie group, right? Because S1 is a Lie group and direct product is also a Lie group. And you can consider in here the following set, e to the I theta 1, e to the I theta 2. So, well, you can maybe even like this. You can take some parameter t here and something times this parameter. And here t runs over reals. So this is subset in here. And if alpha is irrational, so, and this is subgroup, and actually with manifold structure coming from R. But if alpha is actually irrational, then this thing, it is dense, right? So let us call it somehow. Maybe W, because it's called irrational winding of torus. Then W is dense in torus. So picture looks like this. So you have torus, and you have winding which never. So it's not periodic. So it's very, very dense, right? And close. If you pick any point, right, you can, by going far enough by this parameter, you can go closer, like as close as you like to this point, right? And if you consider some in subspace manifold, what is going on in some neighborhood, right, you will get something, always something very, very, like a lot of intersections which are very, very close to each other and dense in here, and you would never get picture like this, right? And you see that this thing is actually not locally closed. Right, so this is an example of something which will be important for us. Such things we will call virtually subgroups. But actually, it is important for other reasons to distinguish them from something which is really submanifold for various reasons. And so when we say it's Lie subgroup, we would like to avoid such thing and see really something like this. Okay. So how to actually to find Lie, like this is one example, but how to find more Lie subgroups. So this is a criterion of what finding submanifolds actually. So suppose that you have, let's formulate it as proposition. So suppose that you have f. It is a function from one manifold to another. So and this is a smooth function. Smooth function. such that of constant rank, So meaning that rank of D. So this is a linear transformation at each point x. So this is actually some number r which does not depend on x. It's for this is for each x and x, right? Then pre-image of a point, right? Pre-image. So if I take y, which is f inverse of z, so z is an element in y, and this leaves. So this leaves. Z, oh, sorry. Z is an element of z, capital, and this lives inside x, of course, right? Then this is a submanifold in our sense. And we will use it. So this is just something from the theory of smooth manifolds. I'm not going to prove it. There's some standard material. I'm going to use it. So in particular, I can consider group SLN, okay, inside GLN, okay. So these are all. So this is a subset of all matrices, right? A in GLN. So the determinant is not 0, but also I would like it to be more specific. I would like determinant to be 1. So this is what's called special linear transformations. GL stands for general linear transformations. And so I claim, so this is a subgroup. And I would like to see that it is actually Lie subgroup. Another example, so this situation doesn't happen, and I would like to use this proposition. So, of course, it's clear what should be f, right? So, by definition, SLN is just a pre-image of one of smooth function which is determinant, right? So we actually have this function determinant. This is from GLM k to c star, and SLN is exactly the pre-image of 1. So we need to see that determinant is a map of constant rank. So this is all right. So GLN is n squared dimensional. This is 1 dimensional, right? So we actually would like to see that at every point, differential of determinant is of rank 1. And this will prove us that this is Lie subgroup. All right, so how to compute differential? So we take differential of determinant at some point A, right? Well, this is n squared by 1 matrix, right? And it is labeled by 2 indices ij that run from 1 to n, and it is just a derivative of determinant of a plus x by dx ij, where x is a matrix of this variables xij, x11, x1n, xn1, xnn. And also I take derivative and take then all xij. So I take derivative and then all x just to be 0 after taking derivative. So it's easy to compute the result. So actually, you just need to compute linear in xij term in here, and this will be the result. So linear term is exactly the minor of matrix A, n minus 1 by n minus 1 minor, which of a submatrix which is obtained from A by crossing out ith row and jth column, right? So so these are minors. So all n minus 1 by n minus 1 minor of A. And if they are all 0, the determinant of A is 0, but we know that A is a matrix from GLN and it doesn't happen, right? So therefore, at least one such minor should be not 0. And therefore, this n squared by 1 matrix has rank 1, right? So therefore, dA determinant ij has, so actually this matrix has rank 1 for every A in GLN, and so therefore this is a map of constant rank, therefore its pre-image is submanifold. We know that this is subgroup, so there we conclude that SLN K is Lie subgroup of GLN. Well, these are already very important examples to study. They're very non-trivial. Already a lot of scientists already work with these Lie groups. So now let us prove something. Important property that we will use in the second lecture is that is formulated in the following proposition. Let us prove that if H inside G is a Lie subgroup, then H is closed in G. This will be important for us because we will consider quotients of G by H, and and closedness is important for this to be Hausdorff space. Otherwise, we cannot talk about G quotient by H as a manifold, and which would be very sad. But actually, H is closed if it is Lie subgroup. So this is why sometimes what we call subgroups here is in some books is called closed Lie subgroup, and this and all and more general subgroups, which we'll call virtual Lie subgroups, sometimes are just called Lie subgroups. So be aware of such terminology in different sources. Okay, so let's prove it. Proof goes like this. Just from the definition of being a submanifold, it follows that H is locally closed. In G. That is, there exists, so for every H, there exists, so for every H, there exists neighborhood of H, U, and G. It's open, and H is inside, such that intersection is locally closed. Is closed. Sorry, we're defining what is closed, so I need just closed here. So intersection is closed is closed in U. Right. So your in the definition, right, of submanifold, we had this well, chart, right, which comes with an open set, right, with this slice condition. And so you just can take this U, this chart, and U intersect with H will be just diffeomorphic to some Km, where M is less than dimension of, where M is dimension of H and N is dimension of G, right? So this is just direct consequence of what we call submanifold. All right, but then there is a not very hard exercise in elementary topology. Which implies that if H is locally closed, then, like this condition, right? Then H is open in H bar. Right, so if you take some G for any G in the closure of H, of course, by continuity of multiplication, GH, any point of this is inside H bar, is a limit point of H, so it's inside H bar. And moreover, since H is open in H bar, then GH, right, left multiplication by G is a continuous map, right? So this also is open in H bar. Well, moreover, it's this is left multiplication is diffeomorphism, right? So it is pre-image of open is open and image of open is open. So that is why. So sorry, GH in H bar is open. So no sign like this. And now we use some trick. We just can write down h as h bar without the following union. So gh as g runs over h bar without h. Of course, you throw away all everything that is in here but not in here. You just need to check that you're not throwing away something which is inside h, right? But so if g is not in h but in h prime, then gh is not in h because h is subgroup, right? So this should work. And this is open in here. Union of open is open, so h bar minus some open set is closed. So this is closed in h bar. And therefore, so h is open and closed so open and closed in h bar, right? So therefore, h is h bar. Well, of course, if something is open and closed in some submanifold, then it is a connected component of this submanifold. But since if you have just a connected component, by closure of this connected component, you cannot get everything, right? So this is why we conclude this, right? And so therefore, h coincides with this closure, so it's closed, and the proof is done. Okay. So next notion, very important. So we defined our objects. What is sub-objects? Now we need map between our objects, which are homomorphisms of Lie groups. So by definition, and definition here is very understandable what it should be, right? If you have two Lie groups, then a map phi from h to g is called a homomorphism of Lie groups. And since we talk always about Lie groups, we usually will say just homomorphism, right? If, so it's called homomorphisms of Lie groups, or further homomorphism, if it's a smooth map and it is homomorphism of groups, right? So it just respects two structures that we have in our Lie group, right? So if first of all phi is smooth and second phi is a homomorphism of just abstract groups. It takes multiplication to multiplication. Okay, and so let us see some examples. One example is that, of course, if you have Lie subgroup, then inclusion map is a Lie group homomorphism. Well, this is in a sense a stupid example, but we'll need to spell this out just to, just we'll use it in proofs a bunch of times. Well, not stupid example is this one. I can construct homomorphism from K to K star, K being R or C. How does it work? It just takes X and maps it to the exponential of X. Right? And similarly, you can take R and map it to S1, right? So this is actually universal cover of S1. How does it work? You take T in R and map it to e to the 2 pi I t. Another example, we already have seen it. It's a determinant. So take it is from GLN, right? So determinant of product is product of determinants, and determinant is smooth function. It's just a polynomial in entries, right? So it's from GLN to the field without zero. And two fundamental questions that we about to answer, maybe not in this lecture, is if I have a homomorphism of Lie groups, what can I say about kernel and image of this homomorphism? Is it Lie subgroup or not? So if phi, so this homomorphism of Lie groups. So question, kernel of phi, is it Lie subgroup and image of phi, is it Lie subgroup? Because it will give us more examples and more instruments to prove stuff. And question is, so answer to this question, just I can give it to you now, but we'll prove it later. So answer for the first one is yes, and for second one is not, no, not necessary. So because image of phi can be something which is not Lie group but virtual Lie group, as in our example for irrational winding on torus. Okay, so to prove first one, we will need and get actually much more examples of Lie subgroups and hence Lie groups. We'll need an action of smooth action or Lie group action on a smooth manifold. So, okay, definition. Let G be a Lie group and let X be a smooth manifold. Then a map from G times X to X is called Lie group action. If, again, alpha is just group action in the sense of abstract groups, is group action, right? Just to recall what it means that alpha of G of alpha of h x is the same, so as, well, we're talking about left actions here, but we can define right action. So left action means that this. So this is just a statement that alpha is a group action. But also we would like alpha to be smooth. Alpha is smooth. Examples. So very important examples is when X is group itself, and group can act on itself in different ways. It can act by multiplication from the left. It can act by multiplication from the right and pre-composed with inverse. It can act by conjugation. Yeah, by the way, just some notation, right? If I have an action, I will write something like G acts on X, right? And this means that I have such alpha. Also, I will use dot, right? So if I have some element of X, some G, then G dot X is just alpha of Gx, right? And this is what I used here, this dot. It's just some standard notation. And second, very important example is that if I have homomorphism from G to H, then G acts on H as follows. G dot H is you map first G to an element of H by phi, and then multiply from left. Well, you can multiply from right inverse or conjugate also, but this will be usually what we will use. Okay. And the last statement for this lecture that we are going to prove is the following theorem. And this will give us a lot of new Lie groups. Suppose that G Lie group acts on a smooth manifold. So this is a Lie group action. Then for every point in X, stabilizer of X, Gx, what is it? It is everything that doesn't move, so all elements on G, such that G acting on X does nothing. Then Gx is a Lie subgroup. Is a Lie subgroup in G. The proof is relatively easy. So let us define this. So let us fix some point and define map alpha X. This is map from G to X, which works like this. You take an element here and map it to the point where X moves under the action of G. And then alpha of X is smooth map. then gx, stabilizer, is exactly the preimage of this map of point x. And so what is left to prove is that alpha of x is of constant rank. Right, so want to see the following: alpha x has constant rank. Okay, let's see this. So let me take, so constant rank means what? That D at some point G1 rank of this matrix equals to rank of this matrix G2 alpha x for any G1 and G2 in G. Okay, let me now consider group element G, which is G inverse G2, right? So I multiply G inverse, so okay, let me be more specific. No. So let me take some G, which is G2, G1 inverse, right? Then what I want from this element is that I can get G2 from G1 by multiplication from the left by G. And then I have this, well, okay, I can consider this map LG. This is exactly the left multiplication by an element G, this one. So this is from G to G, right? And I take H and map it to GH. Very well. Then I have this commutative diagram G, G, X, X. So I can go from G to G by LG. I can go from G to X by alpha X. Here also by alpha X. And I need some map here that I will call beta G to make this diagram commutative. Then it's not hard to see that this beta G should work like this. It takes point X and gives me G dot X. Then this diagram is commutative. Okay, so since it's commutative, I can, commutativity is just this. It's just beta. So if I first apply alpha, then beta, so alpha X, then beta G, is the same as if I first apply L and then alpha. So this is exactly the commutativity of this diagram. And then let me just take differential of both sides. Then I have what? Differential of beta G, differential of alpha X equals to differential of alpha X, differential of LG. Well, we need to put points here. So we start, this alpha is the first one, this one. So we start with the point G1, right? To get to the point G2 by multiplication by this map LG, right? So G1 should stay here. Then when I apply alpha X, I get to, well, here G1 point X, which doesn't really matter. What matters is what stays here. So when I take, so first I apply it again to G1, multiplication from the left gives me G1 is G2, so I should take G2 here. And we're comparing ranks of these two matrices. And we know that these two compositions are the same. Also, we know that DLG and D beta G at every point, these are linear isomorphisms. So these are invertible linear transformations, so isomorphisms. And this means that I can actually take D G2 alpha x and write it through dg1 alpha x as follows: d beta inverse d beta g dg2 alpha x dg1 lg. Anyway, so these two things have the full rank, right, which is dimension of G. And so therefore the rank of this equals the rank of this. And this is exactly what we needed. So conclusion is that we exactly have star. And so therefore you did this map has constant rank. Its preimage, which is stabilizer of the point x, is Lie subgroup. Okay, so important remark is that using this, so we proved the theorem. Important remark is that actually we can compute, knowing the rank of alpha x, we can compute dimension of gx. Namely, codimension of gx equals rank of alpha x. And this just part of constant rank theorem, which says that the preimage of the map of constant rank is manifold, submanifold, and another part in this theorem, which well, you can read in any standard book, is that its codimension is exactly the rank of this map alpha x. And we can use it now to compute dimensions of Lie groups, which is not that trivial. And okay, so let us just enjoy some application of this theorem. In particular, I can consider orthogonal transformations of Kn. So these are all elements in GLN. Well, if I talk about, well, still I can put K in here, such that A transposed is E. So, well, I is the identity matrix here. So this is just by definition what it means for A to be orthogonal matrix, right? So this is a group of orthogonal transformations. The question is it Lie subgroup? Of course, you can answer this question, I guess, straightforward way, but it's kind of cumbersome to go through all the computations and computing differentials. You can do this, but it's not that pleasant. But we'll use this theorem about stabilizer. So we need some action, and we have GLN. Let us act by GLN on matrices with n by n matrices. How? So this is a vector space, of course, and action is like this: A acts on B. So this is also n by n matrix, but we can actually act by this: A, B, A transposed. This is a smooth action, easy to see. And then ON is exactly the exactly the stabilizer of identity. So ON is exactly then G stabilizer of identity with respect to such metrics. All right, and we automatically get that that ON is the Lie subgroup in G1, which is, we didn't even compute any differentials, we just used the theorem that we proved. And second, we can actually answer one of the two questions about homomorphisms. So if I have homomorphism from G to H, right, then, kernel of phi is exactly stabilizer of, of identity in H, right? So G actually then acts on H as we figured, right? As follows: G dot H is phi of G times H. And then kernel phi is exactly the stabilizer of identity in H. And this means that kernel, again applying theorem, is a Lie subgroup of G. Again, we got it for free, just applying our theorem. Okay, so let us wrap up the first lecture at this point.